Okay, so let's provide a brief outline and review of the RSA that we discussed in class. So let me see, this is, let's see, Alice house, which is a lake where, let's say, assume that she is posting her public key. So in her privacy, she selects two primes, P and Q. They assume to be large primes, and they still have to satisfy some technical conditions, but will not be concerned with now. So P and Q are large primes. The idea is that the number n, which is the product P times Q, from the perspective on outside of server, is in almost for all practical purposes impossible to factor. So this n is posted publicly, so it's publicly available, this RSA number for Alice. Now, in the privacy of her space, she calculates the Weatherford function phi of n, which will be the formula as we discussed, p minus 1 times q minus 1. And she selects a number e between 1 and phi of n with no common factors with n. So GCD of e and phi of n equals to 1, which makes e invertible mod phi of n. And then she posts the number. So e is the public encryption key. Now, it's about time to use one of the two important algorithms we discussed. At this moment, she can use the extended Euclidean algorithm, and she calculates D, which is E inverse modulo phi of n. D is a private decryption key, and of course can stay in the house. So Bob on the other side, is a smaller house because it doesn't have to do too much. Okay. So there's Bob. So this is Alice's house, and there's Bob. So this Alice sets up the RSAs. This is what Alice should do to set up. So sets up the RSA. Now, once she sets up the RSA and she publishes the RSA number and the public encryption key, Bob looks up, right, those things, and let's assume Bob wants to send a message over to Alice, and he wants to encrypt that message. So wants to send a message m equals to is a number from let's see, m from 1 to n. Now he looks up at the RSA number, and if the message is large enough, not to fit in this box between 1 and n, Bob will split the message into smaller pieces, and each piece will fit between 1 and n. And then, without loss of generality, we may assume that the plain text is between 1 and n. So n is the plain text. Okay, to encrypt the plain text, so now we got another important algorithm to be used, is a fast exponentiation. So Bob will erase the plain text, the public encryption key of Alice. So and guess the cipher text is m to the power e mod n. There's the cipher text. And this ciphertext will be sent over to Alice. Okay, Alice, let's see what she's doing next. So now the second part of Alice activity. Let's say Alice 2. She receives the ciphertext C. to decrypt, she just raises C to the power of private decryption key. To decrypt as follows: C to the power D mod n. And then it can be proved that the decryption of the ciphertext produces exactly the original plain text that Bob was intending to set. So let's try to say a few words about why this works. Okay, so why this works. So Alice to decrypt, she raises, so again, let's give Alice 2. So she decrypts C to the power D, right? Mod n. But C is the ciphertext she receives from Bob, and this will be n to the power D, n to the power E. So there's the ciphertext, everything to the power D mod n. This will be, by the law of exponentials, n to the power ED mod n. Now, note that D is E inverse modulo P of n, by the way it was designed. So that means D times E equals a multiple of P of n plus 1. That's what it means being 1 modulo P of n. Multiple of P of n plus 1. So with this information, let me go back into the main course of the formula, and this will be n to the power k times P of n plus 1 modulo n. And this will be, again, using some elementary exponential properties, m times n to the power P of n, everything to the power k. Okay, so inside of this bracket, due to the Euler theorem, assuming the greatest common divisor of m and n is 1, GCD of m and pq equals to 1, which for all practical purposes it is satisfied. Right? What are the odds of picking up a random number m between 1 and pq for that random number to be divided by one of the two large primes? Is very small. So let's assume for all practical purposes that GCD of m and pq is 1. The full proof without any simplifying assumption was included in another small video. So by Euler theorem, this is 1. So m times 1 to the power k equals to m, and that's why Alice recovers the plain text. Now let's give a concrete example. Okay, so concrete example, let's see. Alice is p equals to 7 and q equals to 11. Okay, and then n will be 77, that will be public. Anyway, mark these elements which are public, and the ones which are not marked are not public. Phi of n equals to 6 times 10, p minus 1 times q minus 1, which would be 60. And then let's select a number between 1 and phi of n, which is relatively prime to phi of n. Let's say a equals to 13. And a equals to 13, again, public. Is a public encryption key of Alice. Okay, what else is Alice doing privately? So she will invert 13. So she applies EEA to invert 13 mod 60. So let's do the remainder quotient x and y, the table for the inverse. Okay, so let's see here. Remainder, so big number is 60, small number 13, nothing at the beginning, 1, 0, 0, 1. Here's the column of 60, here's the column of 13. Okay, how many times is 13 is 60? 4 times remainder 8, multiply and subtract. I'll get a 1 and a minus 4. So 1 time remainder 5, multiply and subtract, 1 and minus 1 and 5. 1 time remainder 3, 2 and minus 9. 1 time remainder 2, minus 3 and 14. 2 and 3, 1 time remainder 1, 5 and minus 23. 1 and 2, 2 times remainder 0. At this moment, the extended tubular algorithm is over. And look at the y component just below the number you want to invert, was minus 23. So 13 inverse mod 60 equals to minus 23. So v will be minus 23, which will be how to make a negative looking number positive by adding a suitable multiple of the modulus. So just add 60, will be 37. So she applies EA to invert E, and she gets V equals to 37. So for all practical purposes, she is all set. Now let's look at Bob. So let's say Bob wants to send the message M. I'm choosing like a message here to be convenient to calculate. Is 27. How to encrypt? The ciphertext is 27, message to the power, public encryption key, which is 13, modulo the RSA number 77. And let's make a table for the fast exponentiation, k versus 27 the power k mod 77. Let's remove some lines here. So in the left column we start with 1 and 27. At every step, the procession in the left column is double, and the procession in the right column is square, modulo 77. So 27 squared is 36. So you just verify everything here because I just did the calculation myself. So double and then square to 36. So 36 squared modulo 77 is 64. And then finally double 64 square modulo 77 is 15. We are done with this part. Then raising the power 13, we have to write 13 in base 2. So that amounts to a greedy algorithm and express 13 as the sum of items in this column of 1, 2, 4, 8. So 13 equals to 8 plus, what's left is 5, plus 4 plus 1. So then 27 to the power 13 by the law of exponents is 27 to the power 8, which will be 15, times 27 to the power 4 is 64, times 27 to the power 1 is 27, again mod 77, and all of these we'll calculate it and use calculators, and you double check everything, you get 48. So the ciphertext is 48 by using the fast exponentiation or repeated squaring, by the way. Okay, so Bob wanted to send a message numerical value 27. He encrypts the message by using fast exponentiation. The ciphertext will be 48. So C will be 48. Let's write down my computer. Fast text. That's how we get C. Now, Alice 2. So Alice, the second step. Alice 2. So she receives 48 from Bob. And to decrypt, she raises ciphertext 48, the power her private decryption key. So decrypt king C. So 48, which is C, to the power 37 modulo 77. That's what she wants to calculate. Okay, so it's another fast exponentiation. Let's do a table. K versus 48 to the power K mod 77. Okay, 1, 2, let's see, we have to calculate the power 37 now. We have to go up until 32. 1, 2, 4, 8, 16, 32. 48 the power K is 48, the power 1 is 48. So in the left column, we double every step, which gives us the powers of 2. In the right column, we square every previous value modulo 77. So 48 squared, we get 71. Again, you double check those things. 71, 36, 64, and then we'll get 15, and then we'll get 71. Now, you see here we got, if we had continued, then after 71, we have got again 36, so everything cycles this moment. So it's an example, nice example of a cycling in this fast exponentiation algorithm. Okay, so that's the first step. The second step, express 37 in base 2, which can be rephrased as Greeley algorithm with those powers of 2. So 37 equals to 32. What's left? It's a 5, right? Pick from here is a plus 4. Pick the maximum item plus 1. So then this one implies 48 to the power 37 equals to 48 to the power 32, which is 71, times 48 to the power 4 should be 36, times 48 to the power 1 should be times 48, everything modulo 77. And guess what? This will be exactly the value of the original plain text that Bob sent over to Alice. It will be 27. So this will be L. That's how, by looking at just as a result of this toy model, so we show that RSA works. Okay, then double check. I mean, review the in the comment section the proof that the decryption produces the original plain text in all cases, including the very unlikely case in which the plain text we choose accidentally has common factors with RSA modules. But in that case, if we just do like a just in case, check the GCD between the message M and the RSA number. Theoretically, it could happen with a very highly unlikely but very low probability that we just bring the RSA. Okay then, that's all for the RSA outline.